All right. Well, let's start. So I was expecting to see 66 people here. I guess the other, 41 are watching online. All right, so we'll continue the revision lecture from Monday here, cover a few topics that we didn't really have time for, and a couple of questions that people have asked in the meantime. So on Monday we talked a lot about recursion, and we looked at some problems that we could solve using recursive algorithms. We're not going to revisit that. We talked about test cases a little bit briefly, but still I guess we're done with that. Now, one other question that someone had asked was for some more details about static in Java. So we'll start with that and then have a look at multiple choice questions and some I/O questions. So as you've probably noticed, in Java we can declare class members of different kinds, so fields, methods, and also nested classes in a class as static. And that has a number of different effects. So the one that you would perhaps be most familiar with is this idea of a static context, which is the compiler will sometimes throw up an error saying you can't do this in a static context. So static context means that there is no this, right? So whenever you call a method on an object, we have this keyword this, which gives you a reference to the object that you call the method on, right? But when you call a static method, you're not calling it on any object. So it's this has no value in that, and that's called a static context. So for example, the main method of any Java class, the one that you sort of run when you run the class, is always static, right? So that's because when you start off your Java program, you haven't created any object yet. So if you want to do something on an object, the first thing you do in the main method is to create the object that you want to do something on. But static also has some other effects. And in fact, this might explain why it's called static. Static is the opposite of dynamic, right? And this is because we talk about dynamic and static method dispatch, or this is also sometimes called polymorphism. So this refers to how the Java virtual machine determines what method gets called when you call a method, right? So remember that when we have an inheritance hierarchy of different objects or different classes, then we can override methods. We can have a default implementation of some method in one class, and then a class that inherits from that class can override that implementation and provide a different implementation of the same method. So with normal methods, we have what is called dynamic dispatch, which means that when we call this method on some object, the Java virtual machine will look at what is the type of this object, what class does this object belong to, and based on that determine which method gets called. Right. So a simple example of that, which you might have seen somewhere, is that you have the toString method, which is actually declared in, if I'm not mistaken, in the root class object in Java. Java lang object declares a toString method and has an implementation for that. But you often override that when you define new classes, so you define your own toString method. And if you just take any object and call toString on it, it will call the most specific toString method that is appropriate for that object. Now, with static methods, the dispatch is based on the type of the referring variable, not on the type of the object. So you can so remember that inheritance creates a relationship between different classes where subclasses or objects of a subclass can substitute for objects of a parent class. or ancestor class, which means that if we have a variable of a particular type, let's say in extreme example, let's say we have a variable of type Java Lang object. Now this can hold a reference to any kind of object. And so as I said, the dynamic dispatch means that when we call a method on that object, or on the object that the variable is referring to, then based on the type of the object that the variable is currently referring to, we decide which method to call. But with static, this is based on the type of the variable that is referring to the object. So perhaps you haven't done this very often, and I'll show an example in a sec, but usually when you call static methods, you actually qualify them with a class name, right? If you want to call, say, square root on the math class, then you could write math.square root, right? Or sqrt. And that sort of directs you directly to the right method. But if you have an object of type math, you can also call square root on that object, right? So you can call static methods on an object, but the effect of that will be, one, they will be executed still in a static context, which means there is no this, and the reference will be resolved based on the type of the referring variable. So this is all a little bit abstract, and I'm going to step through an example here, which is very much inspired by examples from this Eccles book, Thinking in Java. It's pretty good at explaining these things. So here we define a little class hierarchy, and just to point out, I'm not sure if we have, to what extent we have mentioned this, but when you create a Java file, right, you can actually put multiple classes in this file. The restriction is that you can only have one public class per file. So here we have just one file, and in this we define a couple of different classes. We have a class here called shape, which is sort of represents a general shape of some sort, and we'll look at a bit more in detail at it. And then we have a couple of subclasses, triangle, square, and hexagon, which are sort of different specializations of shape. So all of these subclasses extend shape, right? Now, what can we do with our shape? Not very much. We have a constructor. The constructor assigns every created shape a unique identifier. And then we have two methods here. One of them is just a standard toString method, which will print out, well, or give us a string that we can print out to show the shape. And the other one is a static method called makeNew. And what makeNew does is just that it returns a new shape. So it creates a shape object and returns it. Right. Now, these methods are overridden in all of the subclasses. So let's look at just one of them, triangle, to see what that does. So the toString method in triangle prints, instead of just saying this is an unknown shape, it says this is a triangle, and then says what ID it has. I'll get back to that counter in a second. But also note that the makeNew method in triangle doesn't return a new shape, it returns a new triangle, right? And in the same way, the makeNew method in square returns a new square. And same with hexagon. Okay, so that's just that little background to see. So let's just focus on that part for the moment and see what happens here. So here, main, as an example here, we're creating a little array of shapes, and we instantiate an array of 4 different shapes. We instantiate it with one triangle, one square, one hexagon, and another square, and then we print out the array. And then we create a new array called new shapes, and then we instantiate new shapes by calling makeNew on each of the shapes in our initial array. So the first element of new shapes is going to be whatever the first element of shapes.makeNew returns, right? and then we print out the new, and the second will be what the second element and so on returns. So let's run that and look at the output and see what that tells us. Actually, I don't know if we can just run. Yep. Okay, so the first line here is the print array, where we print the first array. So again, we can just look at what's happening. So remember, we created a triangle, a square, a hexagon, a square, and printed that array. So as you would expect, the output here is that we have a triangle, a square, a hexagon, and a square. And ignore the IDs and the counters for the moment. We'll come back and talk about them in a second. And then we created this new array. Oh, wait. Now the ID did something funny. There. And then we created a new array, and we filled the new array by calling make new on each of the objects in the original array, right? And what we can see in the output here is that the new array contains just unknown shape, unknown shape, unknown shape, unknown shape, right? So that means that the all of the objects in the new array are instances of this parent class shape. So they're not instances of triangle, square, hexagon. So, and this is because of the difference between dynamic and static dispatch. So if we go back here again, we can see that, oh, we don't see it actually because it's hidden in the print array function. But the print array function will call toString on each of these objects, right? Now we have declared this to be an array of type shape. So all the variable that is holding a reference to each of these objects is of type shape. So when print array calls toString, because toString is a non-static method, we get dynamic dispatch, which means that we call the toString method of the object that we're currently referring to. So when we have a variable of type shape that is referring to an object of type triangle and we call toString, we get the triangle's toString method. And that's why we see it printing out triangle. Now with static methods, as I said, it's based on the type of the referring variable. So here when we have a variable of type shape holding a reference to an object of type triangle, for example, and we call the make new method, which is static on that reference, then we get the make new method of the type or the class of the variable. So the general shape method, right? Which means that this call here is returning a new shape, general shape object, not an object of the subclasses. So one way to sort of see the difference here, we can modify this a little bit, is to say we could do a try triangle. So we'll need to catch class cast exception, and we probably need to do something else here. We can do say then we need an else there. So we're going to, let's try, this is a bit awkward. We need a boolean. Oh no, actually we can do, we can just use the ref variable itself. New shape. Okay, so here we have modified the example a little bit. So here, when we loop over the shape array, the first thing we do is we take shape at index I, and we try to cast that to a triangle. And if that works, we're going to call make new on the triangle object, or on the variable of type triangle that is referring to a triangle object. At this point, we know if the cast did not raise an exception, then we know that the object that the variable is referring to is actually a triangle or a subclass of triangle. Right? If we get an error, we're just going to ignore it pretty much. And then at the end, we just qualify this to say if we didn't already assign the new shapes index I, then we just call make new on shapes I. Okay, so let's see what difference that makes. And what we can see, well, we get some of them are not a triangle, but if we look at this line, which is the output here of the printing the new shapes array, then the first object here is now a triangle and all the others are unknown shapes, right? And that's because here we modified the type of the referring variable. So we're still referring to the same object as we did when we called shapes I.makeNew, but we're changing the type of the referring variable. And because of that, we're changing which static makeNew method gets called. Right? Okay. So that's that. Let's come back to this counter and ID and see what that is doing. So as I said initially, we can declare static methods. We can also declare static fields and static nested classes. So here we have declared a static field in the general shape class, which is a counter. And this is sort of supposed to be counting how many instances of all different shapes are created. And the shape constructor assigns this variable ID for the object by taking the current value of the counter and adding 1 and incrementing the counter afterwards. Right. So that's why when we let's see, when we first create this, we get triangle has ID, the first triangle has ID 0, the next square has ID 1, the hexagon has ID 2, and then something funny happens here, but we'll see why in a sec. Let's step down here and see. So the hexagon, because it has 6 sides, decides to increment the counter by 6 instead of just 1. Now, this is another tricky thing about Java and the way that you construct objects. So when we construct a hexagon, so we call the hexagon constructor, the Java will automatically construct a parent object. So it will call some parent object constructor, right? And because we haven't specified by explicitly calling super, then it will call the default no argument constructor for the parent class. So that means that when we call the hexagon constructor, Java will first call the shape constructor and then continue with the hexagon constructor. So that means that when, at this point here, the ID should already be assigned and the counter incremented by 1. So therefore we increment it by 5. We can just check that that's actually correct. I'm not making this up. Yes. So let's do that. and just run it. Right. So we can see that, remember that we construct them in order: triangle, square, hexagon, square. And so this printout here, the first line, is from the call to the hexagon constructor. So when we enter the hexagon constructor, because the parent class constructor has already been called, the hexagon has been assigned an ID, which is 2, and the counter has been incremented to 3, right? And then we add 5 to it, so that the total is an increment of 6, and that's why the next square gets an ID of 8, right? Now, the next thing you might notice here in this somewhat messy example is that when we print out a triangle or a hexagon, we see the right counter. So triangle has 0 of 9, hexagon has 2 of 9. 9 is just the value of this class counter, the static counter. But the square gets 1 of 0 and 8 of 0, right? Why is that? Well, it's because the square defines its own counter, right? So same as with any other field or method, if you declare a field or method with the same name, or the same, in case of method, the same name and signature as in a parent class, you override what the parent class does, right? So that means the when we do toString here in the square class, we're referring to the squares counter, not the shapes counter, right? And again, the resolution of field references for static fields is also based on variable type rather than object, right? So, and we can see this here with the last part of the example. So here we take the last object from our initial shapes array, which is a square. And we cast it to a square. So instead, we remember that originally we have a variable of type shape referring to an object of type square. Now S here is a variable of type square referring to an object of type square. And then we print out a couple of things. So first of all, we check equality between these two variables. And then we print out first the shapes counter and then the S dot counter, right? And I don't need to run it again because we have the output here already, but let's have a look at the output. So the output that we're seeing here is true, but we're seeing two different counter values, right? So true meaning that these two variables, the shapes, the fourth element of the shapes array, and this variable S, they are referring to the same object. So remember that standard equality is reference equality. So this is exactly the same object. But when we ask one of them, what is the value of counter, we get a different answer from when we ask the other one. And that's because both the shapes and the square define a static field called counter, and the resolution of static fields is based on variable type rather than object type. So that means that because this variable is of type shape, we refer to the shape counter. This one is of type square, so we refer to the square counter. Okay. So that's most of that. The last bit that I want to mention here is just import static, which is I didn't know about. It's a nifty little trick that you have in Java, which is saying that you can import static methods from a class into your own class's namespace, essentially. So again, this is an example that I've pretty much stolen from this book, Thinking in Java. So here we have defined a class called printUtil, which contains a static method called printArray, right? So, and this is what we're using in here. So normally, you would perhaps expect to write something here like printUtil.printArray, like that. And if we did a normal import, that is indeed what we would have to do. So let's see what that says. I think we should be able to do that. Or do we have to reference? They should work. They're in the same package. Not sure why that one is not working as it should. All right. We have to qualify it. All right. So if we do this, we import the class. Then we can refer to the static method in that class by saying printutil.printarray. Right? That's what we normally would do with static methods. And you can see that this is in red because it's a broken reference. This is this is like an unresolvable name because there's nothing in the namespace of this class that is called printarray. Right? Now, if we changed this back to what it was, which was what are you doing here? Import static. So notice the difference is just that we put the keyword static there after import. Then the effect of this is that actually we should be able. Oh no, okay. So here we're specifying exactly which method to import. I think we can also do a star like that. So this is saying import all the static methods from this class into our own namespace, right? And the effect is that the effect is exactly the same as if we had now defined these methods as static methods in this class instead, in the public class. Or in fact, I think in all of them. So I think we can also put, we can probably put a call to print array in here. I don't know if that works, probably not. But you can see that it doesn't highlight in red here, right? So we can actually call the static methods that we have imported from all classes that are defined in this file, not just the public class. All right. So that's that about static. I think that there is a few more things to say about it, also about nested static classes and so on, but I think we'll leave it there and instead look at some other exam questions, because there were a couple of those that people wanted us to look at. So let's find which one is this? 2020 S1. So this is the 2020 semester 1. I think this is the same one that we looked at last time. So a few people wanted us to have a look at these multiple choice questions. So these if you look at these past sample exams, these multiple choice questions typically cover something about threads and complexity and grammars and JavaFX. So some of those things that we have done towards the end of the course mainly, except for JavaFX maybe. So all of the questions are kind of different. I'm guessing that what the question asker was asking for is actually to sort of review the specific questions for each of these, not how you answer a multiple choice question in general, because that should be fairly straightforward. But let's look at some of them. I just want to make the point though that just because some of the past exams have these multiple choice questions on these particular topics, don't assume that we'll have exactly the same type of questions on exactly the same topics on this exam, right? We will have the same topics, they will have approximately the same relative weight, So, you know, if we have a question about, so you can see here, if we have a question about complexity, it's only going to be 5% of the total exam, right? Same as here. But it doesn't have to be in the form of a multiple choice question. It could be somewhere else in another form, just to make that point. Okay, so the first one here is about threads, and I think you find a very similar one on some of the other old exams as well. So here it says, given the following 4 Java code fragments, identify the one least likely to contain a race condition. Okay, so let's quickly sort of recap here. What's a race condition? Right. So race condition is something that occurs in concurrent execution where we have multiple threads and they are all trying to write to the same variable, right? The same field in some method. And this is called a race condition because they're sort of racing who gets there first, or actually what matters is who gets there last, right? Because it's whoever wrote last on the variable is the value that's going to be left there after they're all done, right? And this is non-deterministic in the sense that we don't know exactly how the scheduler will schedule execution of the threads, and we can get very tricky bugs if we are reading from a variable and writing to the variable, and we're assuming that, or either first reading and then writing, or first writing and then reading, and assuming that nothing is happening in between. Because in a concurrent execution context, something could be happening in between. So between the read and write, or between the write and read, someone else could have modified the variable. We had an example there in the workers example where the race condition that occurred was when we did a read of a variable and then increment it by 1, and we saw that it could happen that multiple threads read sort of not at the same time, but 2 different threads read, and then both of them increment and both of them write back. So both of them are seeing the same value when they read. Although the intention was that this should be atomic, that the read and increment should only be done by 1 thread at a time. And the way that we got rid of the race condition was by adding synchronized to the method, the keyword synchronized to the method that does the read and increment on that variable. Right. So in order to sort of answer this question, the thing that we need to remember is that we have, well, potentially multiple threads. I mean, this doesn't actually explicitly say that we have that we're creating any threads, but I think the assumption here is that these might be running in a concurrent context. So remember that the run method is the main method of a thread. That's the thing that gets executed when the thread runs. And that this race condition, or this sort of concurrent access to a variable, can only happen in non-synchronized methods. Right. So let's look at the first one. So here we have, this is very similar again to our workers example. We have the run method here has a loop. It calls increment job number. Increment job number does this where it takes the value of a variable job number, which is again presumably common to multiple running threads, and increments it, so it takes the value and then increments by 1. Right. So we can see that if the run method is run by multiple threads simultaneously, then we could have a race condition here. Right. This is exactly the situation that we had in our workers example. So it's possible here that there could be a race condition. All right. So let's look at the next example. So in the next example, what do we have here? It's exactly the same. What's the difference between A and B here? I can't really put them side by side. The IDE doesn't allow it. But can anyone say what is the difference between A and B? So here's A, and here's B. What is different? The only difference, as far as I can see, they're exactly the same. The only difference is that in B, there is a synchronized keyword on this method, which increments the job number, right? That's the only difference. So again, if we have multiple threads running the run method, then they are not going to be concurrently running this increment job number method, right? Every call to increment job number will be done by only one thread at a time. That's the effect of synchronized, which means that here we wouldn't have a race condition. The only access to the shared variable read or write is happening inside this method, and this method is synchronized, which means that there will never be two threads reading or writing to this variable at the same time. Okay. So in B, it is impossible for a race condition to happen. Right. So let's look at C. So what's happening in C? Again, this looks very similar. What's the difference between A and C? So again, if you remember what the A looked like, or if you can put them side by side and do a comparison, the only difference is that here there's a synchronized keyword, right? Here the synchronized keyword is on this method, work. Now what does work do? Work is called by run. So multiple threads could be calling work at the same time in A. In C, we can only have one method at a time calling this work method, right? Now, is that going to prevent the race condition? Simple yes or no question. How many people think yes? Okay. How many people think no? Okay. A few. All right. How many don't know the answer? Couple. Okay. How many know the answer but do not want to put their hand up? No one. Oh, great. So, yeah, this will not prevent the race condition, because the race condition occurs when two threads are at the same time calling increment job number, right? That's where the read and then write of the shared variable happens. And because the synchronization is on a different method, not the method that calls this one, then this synchronization does not prevent the race condition from happening. Or it does not guarantee that the race condition will not happen. So of course this doesn't mean that it necessarily will happen, but at least we know that in B it's absolutely impossible for the race condition to happen, because we have synchronized on the method that has, the only method that has an access to the shared variable. And the last one. So the last one, again, looks a bit different, but and again, it's a bit difficult to put them side by side. But if we compare, we can ignore. So remember that the only difference between A and C is the synchronized keyword. So let's look at just comparing C and D, right? So if you look at the increment job number method is exactly the same. The run method is exactly the same. The difference here is only in the work method, where this one has, and again, say ignore the synchronized, because in A we don't have synchronized there. So this one has a try catch around the thread sleep, but this one doesn't. So again, sort of the same question, is removing the try catch going to prevent the race condition? And it's the same answer, no, right? Because The race condition only happens here in this method. That's where the access to the shared variable is happening, and well, because we're not synchronizing that one, it's still possible for the race condition to happen. So what is the effect of removing that try catch? Well, it's just that if an interrupted execution exception happens in thread sleep, then here it will just print something and return normally. Here it will basically crash the program, right? So okay, so that was stepping through all of these different variants, and as we saw in B, it's impossible for a race condition to happen. So I guess that sort of answers the question. The question was, identify the one least likely to contain a race condition. Well, in B, it's impossible for a race condition to happen, which makes it pretty unlikely. So our answer here would be that B is the one that is least likely. Just for sort of bit of curiosity here, let's do a little example and modify this a bit and see what do we call it? Now this is going to have a whole bunch of errors, but that's okay. We can fix them quite easily, actually. Let's just say implement runnable, and we need to declare int job number and final int what's called work items 1000 or 100 or whatever, doesn't matter. Okay, so here's just taking that that piece of code and just completing it into a class. Not that we're going to run it, but we're going to do something different here. We're going to do a different change. Well, okay. So apart from the fact that this is going to run forever, so with this modification here, are we going to have a race condition? Well, the answer is a little bit ambiguous, you could say. It's kind of yes and no, because here we still have a non-synchronized access to a shared variable. We will have multiple threads potentially reading and then incrementing this variable at the same time. So same as in the other case, the value of job number at the end of running this is not going to be the same as the number of times that this method has been called, right? Which is kind of what you expect when you read this code. So in that sense, yes, there is still a race condition. Now, that race condition has no effect on the execution of this code, because even though we're sort of potentially sort of, well, not multiple incrementing, actually it's less than multiple, redundantly writing to this variable, so effectively we're stepping it back by one. It doesn't matter because we don't use the value for anything. So here we have a race condition, it just happens to have no effect on the execution. Also, this code will never, these threads will never stop, right? Because here we just return 0, and maybe we should return something else. We return that. So that would cause the loop here to finish on the after the first iteration, or even before the first iteration. So all the things will finish. There is still a possible race condition. It's still possible that multiple threads will increment this at the same time, or rather read and then calculate, each one calculating their own increments and write back. So there is still a possible race condition. It's just that it will not have any effect. It will not have any consequence. Okay. So that's that question. I think if we go to a different exam, we'll see that there are very similar question about threads. So I think we'll skip that one. Shall we? All right. Well, let's take the next one, which is a question about JavaFX. And the way that this question is formulated is, well, here's a piece of code, and then it says, from among the following, select a statement that most accurately describes the output of the code above when the program containing it is run and the K key is pressed followed by the Q key. So then it's saying, well, what will be printed? A followed by K, A followed by K and then Q, A, blah, 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 and a couple of other options. Yep. So one way that you can answer this question is to read the code and figure out what it does. Interesting. I don't know if this is the same. Another way that you could answer this question is by just putting this code into a context where you can run it and then run it as described, right? So I think we have that here. I don't know, is that the same one? Yep, it is. Okay, so here we have just copied this piece of code, put it into a class that is a JavaFX application. Of course, to do this, you do need to do the sort of the setup around. You need to declare a class that is a JavaFX application. You need to set up your libraries so that you actually can run JavaFX stuff and so on. So it's slightly non-trivial to make this happen, but you know, if you don't remember exactly how to define a JavaFX application, just go and copy paste from the empty game classes in the assignment 2, right? Or just copy paste any of the examples of JavaFX classes that we have given you and just take out all the content and just leave the main bit, right? So the main bit is this start method. That's what's going to be run when you start your JavaFX application. So that's where we put this stuff. It says, yeah, it's the same, print A, set on key type, print B, and then stage show is the one that's going to actually launch the application, right? So we could just run this, or we could step through the example and try to figure out what's going to happen and why. I think what we'll do is actually we'll run this and then we'll go back and step through and figure out why whatever happened, just to see, be a bit more clear. Now, do we have a runner for this? Can we do run mcq.main? See if this works. Yeah. So that throws up a window, and then remember, what was the question asking? I'll have to come back to here. So the question is saying we press K followed by Q, and note that it is important here that it's a capital K followed by a capital Q, right? So I'm going to press K and I'm going to press capital Q, right? So we can see what happened. It printed out A, B, K, Q. So then the right answer would be F. A, B, A will be printed followed by B, then K, then Q. Right. Now, why did this happen? As I said, when you start a JavaFX program, the start method is what will be called to sort of launch your application. And then within the start method, you will call stage.show, which is the one that actually throws up the window and gets the whole thing running, right? So what happens within this start method? We do some setup, we set up a scene, but then the first thing that happens is we print A, and then here we set up an event handler, but that doesn't do anything. It doesn't run the event handler, it just sets up an event handler. And then we print B, and then we call show, right? And so you would expect that when this is run, you see the print out A, and then this setup stuff doesn't show us anything, it doesn't do any printing, and then we print out B. Right. Now, next stuff that happens is that when we type on the keyboard in the window that was opened, then this event handler gets called, because this is the on-key typed event that is set here. And what it does is that it prints the character that was just typed, and then it checks if that character is a capital Q, then it will exit the program, right? So when we type the K, it prints the K. When we type the Q, it first prints the Q and then exits the program. Just out of curiosity, we can see, because I am not sure what the answer to this is going to be. Let's see what happens if we put a print after stage show here. And we'll run it again and see what happens. Oh, interesting. Okay, so what you can see is that it printed A, B, and C. And then if we go here and we type something, K and Q, same as before. Okay, so that means, and this is the thing I didn't know the answer to, when you call stage show, it apparently does not do the event loop inside that call. So it will create the window, I guess, and then continue. So we'll leave this method and come back to wherever in the JavaFX framework the event handler is implemented, or like the main event loop. Okay, so that's that example. Again, if you look at some of the other old exams, you have a very similar sort of questions about JavaFX. And I guess the takeaway here is that, well, not just for JavaFX, but for any question that is giving you a piece of code and asking, well, what's going to happen here? There are kind of two approaches to it. You can look at it, you can reason about it, you can try to understand what is going on, or you can just run it and see what happens. There are, I mean, of course, there are dangers with both of those approaches. Your reasoning could be mistaken, but also if you run it, it's not necessarily the case that it's deterministic. So as we said above, with the threads question, we could have done the same thing. We could have just copied those code fragments into a class and run it in a multi-threaded environment and seen what happened, right? But it's not guaranteed that we would have seen a race condition in those cases where a race condition is possible. It could have just by chance not have had one, or it could have had one that we didn't notice, right? So as we saw with the modified example, you can have a race condition where we don't actually see the effect of the race condition. So it's not always sort of just running code and seeing what happens is not always a guaranteed way of answering questions about what can happen when you run it, because it could be different depending on context, or it could just be non-deterministic, so you get different results when you run it different times. All right, so let's go on to the next multiple choice question. So this one is about complexity, and here we have what looks like a fairly complex function. complex in the sense of being difficult to read, and doing something. And the question is asking us, what is the time complexity of this method? Right. So remember that when we talk about time complexity of a method or an algorithm, it's the time taken to run that method or that algorithm as a function of the size of the input. And when we say time taken, what we're really interested in is sort of counting elementary operations, right? So we're not, and we give this in this big O, or order of notation, which means that we don't care about constant factors, we don't care about sort of behavior on small size inputs. It's what's the trend going to be when the size of the input grows large, right? So let's look at what does this method do. So it's taking a list of integers. If the size of the list is less than or equal to 1, we just return the list as is. It returns a list. So it takes a list of integers, returns a list of integers. Otherwise, we're going to keep the size, and we're going to subdivide the list into a left and a right. And we have some indices here, LF, RF. I think they're being used as indices or something like that. And we're going to construct a list called result here. So we create a new array list, which is the same size as the original input list. And then we do a loop here where we say as long as LF is less than L dot size and RF is less than R dot size, if something something, and then we're going to do a so we're going to do a comparison of elements from the left and the right sublist, and depending on that we're either going to add something from the right sublist or something from the left sublist to this result array and increment one of the counters or one of these indices RF and LF. So I mean, the first question you might ask yourself is what's going on here? What is this method actually doing? Not necessary to answer the question, but it might help our understanding a little bit in order to sort of figure out what's going on. So it's subdividing the list into two halves, right? Left half and right half. So the left half is from index 0 up to half the size, up to not including, I'm guessing, and the right half is from half size to full size, right? So it's splitting it in half, and then it's creating this merged result list by looking at the elements of these lists pairwise and comparing them. And it looks like it's going to take, so if the one on the right is smaller than the one on the left, we're going to add the one on the right as the next one in the result list. So essentially we're doing some sort of sorting here, right? What we're doing is we're taking a list, we're splitting it in half, and then we're doing a sorted merge of the two sublists. So that means we're taking the smallest, we're looking at the sort of the current first of the two sublists, and we're taking the smallest one and putting it into the result list. Okay, so how do we determine the complexity of this method? So we said that what we want to do is to count elementary operations. What kind of operations are being done here? Well, we're doing comparisons. Comparisons is always one to watch out for, but here we're just comparing integers. So we can say that comparing a pair of integers is probably constant time. The rest that we're doing is pretty much just moving data around, right? We're assigning, taking things out of lists and assigning them to positions in lists. Couple of things sort of to watch out for whenever we say that we're doing something in constant time, or when we talk about elementary operations, if we're calling methods on other objects, we have to sort of think about, well, how complex are those? What are they doing? Right. So for example, here we're doing add on a list. So remember when we implemented an array list ourselves, whenever we add to a list, we had to, sometimes we had to double the size of the list, and when we did, we had to sort of copy all the data out of the old array into the new array. So potentially, well, in a simple case, when there's plenty of space in the array, adding an element to an array list is just constant time. We just add it and increment the counter. But in some cases, it might require more, because we might need to allocate a new array and copy all the old data. Right. But here we have initialized the result list to be of the same size as the input list. So that means that we're never have the add calls here are never going to have to allocate a bigger array, right? Because we're only going to add as many elements as there were in the input list. So these ones we can sort of safely say are going to be constant time. What else are we doing here that could be non-constant? Any suggestions? Okay. The one thing I would point to is this one and this one, right? We're calling sublist here. Now, if the input list is, and I believe, you'd have to look up the documentation to see, but I believe sublist is going to return a new list, right? It's going to return a new list object that contains the left half and a new list object that contains the right half. So how long does it take to create a new list object that contains half of a list? Well, we're going to allocate an array, assuming it's an array, and we're going to copy half of the contents of the original list over into the new array. And then we do that for the other one, right? So these are not constant time operations. The time it would take us to create those two sublists is roughly proportional to the size of the input list, right? And when we say roughly proportional, translating that into big O notation, that means order of n, right? It's approximately linear in the size of the inputs. Now, the other thing, of course, is that we have a loop here, and every time that we have a loop, well, the question that we have to ask if we're dealing with complexity is, how many times are we going to go around this loop, right? And here we're going to go around the loop until either until as long as either the left index is less than the left list size, or the right index is less than the right index size. Or conversely, that means we're going to stop when both of these index variables have reached the end of their respective sublists, right, left and right. Now, when is that going to happen? Well, we can see that every time we go around the loop, we go either in the if branch or the else branch, and in each of them we increment one of the counters. So we're going to increment at least one of these two counters every time we go around the loop. The initial the size of the sublist is half of the original list, which means that the total number of times is just going to be the the size of the original input list, right? So we have instead of having just one counter that is being compared to the size of the input list, we have two counters, and each of them is being compared to the size of half the input list, but in every iteration we increment only one of them, but also exactly one of them. So the number of iterations of the loop is going to be the size of the input list. So if we put all that together, what does this mean? We're doing we're doing these two operations, the sublisting, which is linear in the size of the input list, and then we're doing this loop, which is also going to be linear in the size of the input list, right? So we're going to do essentially 1, 2, and then 3 operations that are going to be of time complexity linear in the size of the input list. Now, this is sort of another of the arithmetic rules of big O notation, is that if you're doing a sequence of things that each have a certain complexity, then the complexity of the total, if it's a fixed size sequence, so in this case we're doing 1, 2, 3 things that each have a different complexity, well, they have the same in this case, then the complexity of the overall thing will be dominated by whichever one is greatest, right? So if we were doing something that is linear followed by something that is linear followed by something that is quadratic, we wouldn't even bother with the linear terms, because for large enough inputs, the quadratic term will always dominate. So here we have 3 different linear operations, which means that the complexity of the whole thing is going to be linear. So that means the right answer here should be C. So the complexity in the size or in the as a function of the size of the input is order n. Yes. Oh, did I miss something? Where does it go back to calling? Ah, right. Sorry. Yeah. Okay. My analysis is completely off then. Yeah, that's right. There's a recursive call there. Okay. Fair enough. That makes the question a little bit more difficult, but okay, let's step back and do the whole thing again. So yeah, I totally missed that we're calling f here. And that does change the picture a little bit. So so how are we going to work this out then? This gets a little bit more complicated, but okay, most of our analysis so far is still fairly correct, I think. So we just have to, instead of saying that we're doing these 2 things that are linear, we're doing something that is whatever the complexity of this one is on half the size input, right? So how are we going to work this one out? This is one of those ones that are going to be somewhat difficult. Okay, let's put this into something here, just so we can type it down and type some stuff around it. Okay, MCQ. Okay. Right. Just going to put that in here. Happy with that? Oh, we need an array list as well. Okay, so here we're calling we're calling recursive. Okay, so now in order to sort of analyze what's happening here, I think we need to write something down. So let's do that. So if we're calling f on a list of size n, right, then what's going to happen is that we are going to do f on n half, that's calling f on the first sublist, and then we are going to do f on n half on the second sublist, and then we are going to do the loop, which we concluded is linear, right? Okay. We shouldn't use f here. All right, we'll call it tf for time of f, right? So so it's going to look something like this. Now, how do you do this one? And the other thing that we know is that if we have 1 or less than 1, then it's going to be constant, right? Because we have this case where if the input is 1 or smaller, we're just going to return straight away. So this gives you a set of recursive equations. You can solve these in a couple of different ways. How do you do that? Let's see, you can rewrite that so that you have all the yeah, so been a long time since I did this. There's a couple of different ways that you can try to solve a recursive equation like this. I think you can try to basically write it as a if you reformulate it as a sum, maybe you can try to solve it as a sum. But okay, the sort of the basic method that will work if you can't think of anything else is that you guess what the right answer is and then you prove it by induction. That's sort of, well, it's a bit of it's not a very efficient approach because you have to guess the right answer first. But let's say that we try to do something like that. Then the other thing that you can do in this case is that once you recognize what this algorithm is actually doing, what it is, if you remember your algorithms, which you might not, then you would know what the complexity is. So this is an implementation of merge sort. So with that recursive call, as we said, it takes the two sublists, it merges them in a sorted way, sort of, which means that if the two sublists are already sorted, then the end result will be a sorted list. And because we are recursively calling it, then we will indeed have two sorted sublists. So that means that this is merge sort, and merge sort runs in n log n time. So that's one way of knowing what the right answer here is. But I guess if you didn't, you could hypothesize that the answer might be n log n, and see where you go with that. So if we say that dfn is n times log n, then this is true of, well, I mean, I suppose it's true of the base case because it's just constant. It doesn't matter. Any function will be will satisfy the condition that the size, the complexity of a constant input is constant. But then you would look at the induction case and say, well, okay, so if we have 2 times n half log n half plus n, and work out what that would become. So that would become n times 2 log n half plus n, and what can we do with that expression? 2 times, so that's going to be, God, what's that? What can you do with that? So all right. Please correct me if I'm wrong, because this is not at all my strong point here. So addition of logs is the same as multiplication of the arguments, isn't it? So because this is the same as saying log n half plus log n half, which is sort of again should be the same as log n half times 2. If I could be completely wrong about that, but if I'm not, then that gives us n times log n plus n, right? Which again, when we put a big O around it, is the same as n times log n, because we ignore or where we have a sum of a fixed number of different complexities or different factors in a big O expression, then it's only the biggest one of them that matters. Okay, so that would be one way of sort of, well, this is not really working out the answer. This is just proving that the answer that we guessed, n log n, is actually the correct answer. And that's assuming that I haven't made a mistake there. All right. So the question was a bit more tricky than I thought. Let's go back to the actual question. All right. So there's a worst case here, since we had a fixed number of different answers to choose from, we could at least have sort of gone through them one by one and tried to figure out whether or not any one of them would fit as the right answer. So we could definitely have ruled out the last one, because we know that at least the loop has complexity linear, which means that the whole thing can't be log n. We could have tried to prove that it is linear, the whole thing, and see if that breaks somewhere. Well, this one we did, and same with the square. Of course, we can do from the bottom in a sense, because if we had proven that it works in linear time, then of course we don't have to disprove that it runs in a higher time. All right. Oh, well, here's another one. Do we want to do another complexity question as well, or shall we move on to well, there's heaps of them, or shall we do grammars? All right, let's do one more complexity question, because it is a tricky one. It's a tricky thing. Okay, so what do we have here? Let's be more careful reading this time. We have a loop. So we're taking as input a list. We have a Boolean flag, which is set to false, and we have a loop that will run as long as that flag is true. Interesting. Oh yeah, okay. So we have a loop that will run as long as the flag is true, and what happens inside the loop is that we set the flag to false, and then we do some kind of iteration over the whole list, or is it the whole? Yeah, we do an iteration over the whole list, and we do something. If some condition blah blah blah, then we do something, and we set the flag to true. Okay. So essentially, what this is saying is that we loop over the whole list. If we did any modification, yes. Oh, have we lost the projector? Why? Why? Screen. Come on, it's on. Okay, let me try something different just to see. No. Okay. All right. Right. Oh, interesting. Okay. Alright, not sure what happened there, but the projector is back. Alright, so what we were saying, we have a loop. In every iteration of the loop, we're going to loop through the list, and we're going to maybe do something. We're going to do like if this if is true, we're going to modify the list somehow. We're calling set here a couple of times, and we're going to set the flag to true. So that means we will go around the outer loop until we manage to go through the inner loop without doing any changes to the list. Right. So every time we go around the outer loop, we're going to do some change on the list, or the last time around we're going to leave the whole list unchanged and just exit. So what's the condition here that will make us modify the list? Well, we're going to look at we're going to compare element I with element I minus 1, and if, what is this saying? So compare, if compare is less than 0, that means element I is smaller than element I minus 1, and in that case we're going to take one out, and then we're going to swap places, right? So we're going to swap I and I minus 1. That's what will happen here. So that means that if we go through the whole list without triggering this if condition, so without setting the flag to true, that would be because every element is, wait, it's I and I minus 1. So if I is smaller than I minus 1. Yeah, okay. So every element will be greater than the one before it. So for every I, get I will always be greater than or equal to get I minus 1, right? Which means that we will go around this loop until the list is sorted, right? That's so this is another sorting algorithm. Interesting. So this is asking us what's the worst case complexity and the best case complexity as well. Okay. So so let's do the best case first because that's easier. Okay. So what's the best case complexity here? What's the smallest amount of time that this algorithm could require? Or let's say the smallest. Again, we should start by looking at, are there any sort of hidden non-constant operations here? But there's not really, because the only thing we're doing is get and set on a list of fixed size. We are calling compare, so we don't know what the complexity of compare is. So maybe what we should do is just count the number of comparisons. That's a good estimate of the complexity here. So in the best case, what's the smallest number of comparisons we're going to do? So as said, we go around the outer loop until we manage to get through the inner loop without making any modifications to the list, right? So so that means that we have to go around the inner loop at least once. Right? The best case is we go through it only once. If the entire list is already sorted, we just go through the inner loop once, which means we will compare every element to the one before it, which means we're doing n minus 1 comparisons, right? Length of the list. So that means that the best case complexity would be order of n. So, okay, that rules out 2 of the answers. So we don't have a best case complexity of n log n and not of log n. The best case is order of n, right? So that means now the question is, what's the worst case? Oh, that's great. So, okay, so we're down to a choice between A and B. So A is saying, do we have a worst case of n square and a best case of n? And B is saying, do we have an average complexity of n log n and a best case complexity of n? Okay, so now I'm going to say we're going to be a little bit strategic here and say that, well, this is a multiple choice question. We're only given two choices because we have already ruled out 2 of them. So instead of trying to work out exactly what is the worst case and the average case complexity, because especially analyzing average case complexity is pretty hard, we're just going to try to sort of reason our way to saying whether one of these is impossible or possible or impossible. So so let's say, so if we want to say, could it have a worst case complexity of n square? Well, then can we construct a worst case where it requires n square operations, right? Or in particular n square comparisons? Is there such a case that we can think of? I think there's a fairly easy one, which is to say, if we have, let's say we have a list and the last element in the list is smaller than all of the other ones. So if we take that example, what is this algorithm going to do? Well, first iteration around the loop, it's going to loop through the entire list, compare all the elements pairwise. None of them will move because they're all sorted correctly, except for the last one, right? And the last one is then going to swap place with the second last one. And because we did a swap, we set the flag, so we're going to go around the loop one more time. What happens the second time we go around the loop? We're going to go through the entire list. Everything is already sorted, except the second last one is smaller than the third last. Right. So we're going to swap them and set the flag so we go around one more time. So you can see the pattern. This the smallest element that we had put last in the list is going to travel down the list all the way to the beginning, one step every time we go around the outer loop. So that means that we're going to go around the outer loop at least n minus 1 times, right? Or maybe it's even n times, because we're still going to do the last iteration as well, where nothing changes in the whole list. So that's one thing. And then the second thing we can notice here is that the inner loop, the for loop here, is going over the whole list, right? So it's going to go over the whole list every time. So that's again n minus 1 comparisons. So we're going to do, in that case, we're going to do n times n minus 1 comparisons, which is a quadratic number, right? It's, I mean, we can work it out. It's n squared minus n, which again is dominated by the n squared term. So we can say that there is a case where this is going to take quadratic time, which means that the worst case complexity is at least n squared. It could even be worse, right? We have only proven that there is a case here where it's going to take at least n squared time. There could potentially also be cases where it would take even more. Between trying to sort of work out that and so if we really wanted to make sure that the worst case complexity is n squared, we also have to kind of demonstrate that there is no case where it will take more than n squared. And again, this is going to be quite tricky, and I said doing average case complexity is even worse. So at this point, given the amount of time it took us, I would just take a guess on A. That seems to be the best answer here. It matches, we know that it has at least worst case complexity of n squared, and we know that it has a best case of n, because that was easy to work out. Now the average is a bit tricky, but I guess we can do a little bit of a reasoning about the average case as well, just to see if we think that n log n is reasonable. So if we're taking an average, we have to take an average over some set, right? Some population of possible inputs. And so what is the population of possible inputs that we could be looking at here? Well, the reasonable one to assume is to say all lists of size n, right? Or all lists of integers of size n. So out of the space of sort of all possible lists of size n, what is the average? And again, for each one of those lists, that the time it takes this algorithm is going to be determined by the number of times we have to go around the outer loop, right? And that is, I guess you can say, so like in the example that we just talked about, where we had the smallest element at the end and had to travel all the way to the beginning, we can say that the number of iterations of the outer loop is going to be at least sort of proportional to the longest distance that any element in this array or list is from the position where it will be in the sorted list. So if we have something that is in the middle of the list and should be first, then it's going to take at least length half iterations to get to there. And if we have something that is at the end and should be in the middle, again, that will take length half iterations. So I guess the question that we get then is, if you pick a random list of integers, what is the sort of expected value of the maximum distance that any element is from its correct position? And again, this seems to me like a fairly difficult question to answer, but I'm going to venture a guess that it is going to be more like something that is linear rather than something that is logarithmic, right? Because let's say that let's say that we take just our random list and we ask where in this random list is the smallest element. So it has an equal chance of being exactly anywhere in the list, right? Which means that if we double the size of the list, we also double the sort of expected distance that the smallest value has from its correct position. So I would say that the expectation there is going to be that some element will have to travel a distance that is proportional to the size of the list, not to the logarithm of the size of the list. So I would rule out the average complexity of n log n as being sort of probably not true. Well, pretty much certain it's not true. I wouldn't call that exactly a formal proof, but at least it's enough to give you confidence to say that A is definitely a better answer than B. Alright, so as you can see, these complexity questions can be fairly tricky, and they can be, we spend a lot of time thinking about them. I don't know if we want to do one more, because we have just about 7 minutes to go. I think what we'll do is to have a look at a programming question, because so we could talk about grammars for a bit, but also someone had been asking about programming question, and let's see which one it was. Someone wanted to have a look at some of these I/O questions where we have to read and write a file. I think we have one here. Yeah. So so this is from the 2020 semester 2 exam. We have a couple of these different variants of I/O questions. So I think the one that was asked about specifically was checksum. So let's look at checksum and see what it is. What is the question? So it's split into a couple of parts, 2 parts. Right, so we're to implement a method that takes as input. So notice that so we have an input string and an output string, but these are not the inputs and the outputs. They are names of input and output files. So we're supposed to read and write files here. And we have a Boolean argument called checksum. All right, so part 1 says open the specified input file. If the checksum Boolean is false, simply copy all bytes of the input file to the output file. Part 2 covers the case where the checksum Boolean is true. Okay, so we can do part 1, which is, you know, half the marks of the question, by just copying a file, right? So how did we copy a file? We need to do something like a what's it called? It's called a file input stream, I think. In an input stream input and a file output stream out file output stream, output. Did it automatically import the things for us? Yes, very nice. And then we need to read everything from the input stream and write it to the output stream. Okay. So how do we do that? We do a loop. And now the tricky thing to remember here is that there's a couple of tricky things about reading and writing files. Again, if you don't remember these things, just go and look up the API documentation for input stream and output stream, right? Because it's all written down there. But from memory, the two things that we need to know here is that the read operation on input and output stream is read returns an int, but it actually is reading a byte. So we might need to cast that to a byte in order to print a byte to the output, because otherwise if we print an int to the output, then it's going to write 4 bytes, I think, depending on the size of an int. And the other thing is, how do we know when we have gotten to the end of the file? Right. So that's the two things that we need to remember here. So we're probably going to do something like, we're going to have an int which is really going to be a byte, and then we're going to use, I guess, the trick of assigning it byte read equals in.read, I think. It's not equal to -1. -1 is the indicator of end of file. Then we're going to do a byte b by casting this thing we have read to a byte, and then go out dot write the byte. And then we go at the end, we can do in close and out close. So that's what we need to do in the case when checksum is false. Then this is all we need to do. Something like this, right? We're just gonna read byte by byte. Of course, we could do this more efficiently by reading a buffer, using buffered readers and all that stuff, which we talked about in the lecture on files. But for now, let's just see if that actually solves sort of half the question, right? This one. And I think we'll just run, that should run the tests on it, and we'll see if that works. It is complaining about these ones. Oh, we have unhandled exceptions here. We might have to put a try catch around the whole thing. And what else have we got? Somewhere we forgot a semicolon, where did I not do this? Oh, no, I forgot an equal sign. Okay. Alright, let's see if it builds. Boolean cannot be converted to int. Where are we? Okay. Maybe we need to we need to bracket that. and then it's complaining that we're doing, we need to catch exceptions or declare them. I don't think we can declare them because that would change the signature of the method, and then it might not pass testing or something like that. I'm not sure. So I guess we'll just do a catch IO exception. Is that enough? No, file not found. Alright, we'll catch file not found. And just do something like print this is a very bad form of error handling, just printing an uninformative error message and silently ignoring it, but because this is just we don't expect this error to happen in testing, and it's just something Java forces us to do. Let's see if we'll be happy with that. And it's complaining about IO exception as well, so we need to do that. Exception. All right. Alright, so we can see that this passed some of the tests, but failed some of the others. And I think the reason why we passed some and failed some is because here we've only implemented part 1, right? So we're not even looking at what this Boolean variable is, whether we should compute a checksum or not. But at least we're solving sort of part 1. If checksum is false, simply copy the bytes. So we have done that. And with that, I think we are pretty much out of time for this time, and that is, we're out of time for the whole semester. So I think we'll put a more complete solution to this with comments in the lecture repo sometime later today or in the next few days. If you have any other questions about exam questions, of course, feel free to post on Piazza. We'll try to answer some of them. Do try to be specific, so say this specific question, or you know, what's the particular problem you're having with it. Right, that's all. Thank you.